All right, let's get started. So last week we looked at brute force. We finished off brute force. Now we're going to think about the more clever algorithmic techniques for doing problems. So as I told you last week, brute force is good for certain types of problems. So brute force is good for types of problems where you have to enumerate a lot of things, and if you can do it in time, you'll get full marks. If you can't do it in time, you might get part marks. But what happens if you need to devise a more efficient algorithm to do something? Well, that's where the more clever aspects of algorithms come in. And that's what we're going to start learning today. So we've covered brute force, we've covered sliding window problems, which are another type of kind of clever technique, sets, maps, and dictionaries, another clever technique, and graphs, which are essentially a full type of algorithm by themselves, like breadth first search, depth first search, and traversal. These are all just types of algorithms that are very good for solving particular types of problems. So now we're kind of moving on to techniques for being able to solve problems more efficiently. And we're going to start with divide and conquer. So let's get started. So what can I tell you about divide and conquer? So first of all, divide and conquer is essentially a method of solving a problem where you divide the problem into several steps. You divide the problem into several smaller problems. You solve the subproblems, and you combine the solutions from the subproblems to solve the original problem. So let me write that out so it makes actual sense. So divide and conquer. Divide and conquer. So step one is divide the problem into subproblems. And usually these are a portion or fraction of the size of the original problem. Okay? Step two is solve the subproblems. So divide until you get to some sort of base case of some sort of recursive method. And step three is you need to have a way of combining the solutions for the subproblems into the solution for the original. Okay, let me give you an example to illustrate what I mean. Okay? So the example is the classical binary search. That's our first example for today. The classical binary search. So the problem is very simple. Let's say I'm thinking of a number between 1 to 1000, and you need to guess it within 15 tries. Now, if you get it wrong, I will tell you if the number I picked is higher or lower. So for example, let's say my number is 126. Okay? you guess something. Let's say you guess 355, and I tell you that the number is lower, that my number is lower. Okay? Or if you guess 874, oh, well, my number will still be lower. But if you guess, say, 77, I will tell you it'll be higher. There we go. Makes sense? Now, this is a kind of problem that even a child can figure out, simply because the strategy, once seen, is extremely intuitive. All right. So the way we solve this problem, the solution is step 1, guess 500. Okay. So if it's lower or higher, then half the search space. Half the search space. Right? So for example, if the guess is less than 500, do the same procedure on 1 to 500. Okay, so let's say we start with the possible numbers from 1 to 1000. I'm only talking about integers here. We're not talking about real numbers. Like I have an integer number between 1 and 1000. Let's say I start with all of this, right? Guess 500, which is the midpoint of the interval. Okay, we do the same procedure on 1 to 500. So we go back to step 1, guess the midpoint of the interval. Okay, that's 250, right? And if it's higher, if the guess is bigger than the midpoint, our interval is now the midpoint up to the upper bound, right? So in this case, it would be 500 to 1000. That's what we'll be searching now. So let me just do it for 126. So we start with the interval 1 to 1000. Since 126 is less than 500, our interval is now 1 to 500. So this is our subproblem, right? And then since 126 is less than 250, our subproblem is now 1 to 50, right? And then since 126 is between 125 and 250, because we half the search space, we get 125 and 250. Or actually, I should have done it this way. There we go. 125 and 250, and so forth. We narrow down until we get to 126. Okay? The question is, how long does this take? All right. How long does this take? How long does it take? Okay, so this is kind of related to another question, right? So let's say I have, this is an unrelated question, but it's actually very related. Let's say I have some bacteria, and we start with one bacteria and double each day. How many days does it take to get to n bacteria? So we have 1. On day 1, we have 1. On day 2, we have 2. On day 3, we have 4. On day 4, we have 8, and so forth. Day 5, we have 16, and so forth. Right? So how long does it take to get to some number n of bacteria? Right? And it turns out that, well, the answer is going to be something like log. It's close enough to log base 2 of the number, right? Because we're doubling each time. So what we want is kind of the opposite or the inverse of exponentiating, right? So we know that since the bacteria are doubling every time, right? The bacteria are doubling each day. What we want is the opposite, right? How many days to get a number of bacteria, which is the opposite of what is happening to bacteria, which is like 2 to the, this is the pattern here is like bacteria is 2 to the power of the number of days, right? So the days n is like log 2 of b. Oh, sorry, b is, so bacteria, log 2 of the bacteria, the days, right? And that's what we wanted, right? The number of days is approximately the log of the bacteria. And in the same way, it's very similar to our problem, which is like, how long does it take to do the guessing game, right? So what we're doing is we're trying to figure out, we have a search space, say 1 to 1,000, and we halve the space each time. Right? So we're doing something like, we have 100 numbers to search, 1,000 numbers to search, then we have 500, then we have 250, then we have 125, and so forth, and ... until 1. How long does this take, right? But it's exactly the same thing as saying that we have some process that goes 1, then 2, then 4, then 8, and doubles like this, and then reaches some number, right? Do you see how these things are exactly the same? Well, they are, right? How do I explain this? It's just the same thing as going down, halving every time, and finding the number of iterations this takes. It's the same as something that doubles every time and finding how many iterations it takes to get from this place to the other place, right? So the answers are exactly the same. It's just log base 2 of the n, which is the input size. Input size, or largest number guessed in the interval. So for example, for n equals 1,000, for n equal 1,000, it takes log base 2 of 1,000 steps, right? So if we just are searching 1 to 1,000. If the guessing game was on 1 to 1 million, right, it would take log base 2 of 1 million. Let's write 10 to the 6 for short, right? So that's how long it would take. Just to give you an idea, right? Using the change of base formula, log 2 of 10 to the 6 is like log 10 to the 6 divided by log 10 of 2. Pretty sure that's right. Log 10 of 2. I think that's correct. Should be. Yeah, so what we get is around about, I'm pretty sure it's around about 30 operations. Let me just check that. Oh yeah, it's about 20. It's about 20. which is about 20 operations. So now you see why this is really powerful, right? When we had our linear time algorithms, right, like our sliding window problems and things like that, as the number of iterations increased, the as the input size increased, the number of iterations or operations needed to solve our problem also increased proportionally. So 1,000 an input size of 1,000 means it'll take 1,000 operations to solve. An input size of 1 million means it takes 1 million iterations to solve, but not with this algorithm. With this algorithm, it scales with the logarithm, which means that, and because the logarithm is an extremely slow-growing function, our algorithm is extremely fast. So for a case of guessing a number from 1 to 1 million, we can do it with 20 guesses. So 20 guesses. Right? That's pretty amazing. Whereas for 1,000, log of 10 to the 3 divided by log of 2 is 9.96, right? So log 2 of 1,000 is approximately 10. Because 2 to the 10 is 1,024. Just a convenient mathematical fact that you should know. So, yeah, right? It only took us 10 more guesses when the input size went from 1,000 to 1 million. That's pretty cool, isn't it? So this means that the algorithm is O of log n, is the time complexity. Time complexity of this method. Okay, so let's implement it. Just for fun, let's implement it. So here's how we would write this out. So we would define a function. Oh, actually, let's do another quick exercise before we implement it. Just to show you why this is useful, why our guessing game is useful. So another application is searching a sorted list. So for example, I have some numbers. Say I have 1, 3, 4, 7, 11, 18, 23, 55. Okay, this is a sorted list, and I want to search for a number. Let's say it's 3. I want to search for 3. Okay, so what I do is I find the middle element. Okay, find the middle. All right. Let's say it's 7. Is 3 less than 7? Yes, it is. So we splice the list this way, right? So now we're only searching, we're only searching this side, right? So now is 3 less than the midpoint of this, which is, let's say it's 4? Yes, it is. So now we're only searching this part over here, right? Is 3 bigger than 1? Yes, it is. So now our box has shrunk to this part. Our search space has shrunk, and we only have 3 left. And we know where it is in the list. So this is really cool, right? You can find something in a list and know where its index is when the list is sorted in log n time, right? That's a cool application of this guessing game, which is called binary search. All right, so let's implement that, right? So the way we would do that is we would define a function. Let me go back to my Python terminal. There we go. Define a function called binary search. It takes in an array, L and R, which are like the left and the right bounds. So where the start and the end are, like how far you want to search. And X, let's say that's what we're searching for. All right. So here's one implementation of it. While L is less than or equal to R. So in other words, what I'm saying here is while our left and right don't go don't intersect. They don't go across from each other, right? They don't go over each other. While there is still a space to search, while there is still part of the array to search, we define the midpoint. Mid is left plus right divided by 2. Okay? That's the middle. And now we check the middle. If the array of the middle is x, then we've found it. So return mid. Return mid. Now what happens if x is bigger than the middle element? So elif r mid is less than x, right? So the middle element is less than x, so x is bigger than the middle element. Then we ignore the left half of the array. So we go left equals mid plus 1. So we move the left index all the way to the middle, right? In other words, when we were doing our guessing game, when we had 1 to 1000 that we were searching, what this would correspond to is if we had the array of the middle would be, say, 500, and our x was, say, 700. Then we need to search 500 to 1000. So we move the left thing, which was 1, the left pointer, which is 1, all the way from 1 to 501. So we now know that we can eliminate the left half, right? Because of the way the ordering works. Okay? Similarly, else, I'll just write it out. If elif r mid is bigger than x, r equals mid minus 1. And if we can't find it, return minus 1, meaning the element is not present in the list. So that's binary search. You can search a sorted list this way, and it will work. So let's go through one other simple application of divide and conquer before we get to the kind of harder problems. All right? Let's be quick about this, and then we'll cover something a little bit harder. All right? I know you're itching for something a little bit tougher than guessing numbers from 1 to 1000. So we will get there. Okay? So here's another application. So let's talk a little bit about sorting. All right? Sorting lists. Right? So this is an algorithm called merge sort, and it essentially sorts lists quite quickly. So here's the idea. Let's say I have an unsorted array. Let's say 5, 3, 8, 4, 7, 9, 6, 1. Okay? This is an unsorted array. Unsorted array. Okay? The idea is, imagine we could divide this problem. Our problem is to sort the entire array, right? Our problem is to sort the entire array, right? Let's say we had some sub-problems, which is to sort the left half of the array and to sort the right half. Okay, so sort 5384, sort 7961. Okay? The question is, can we combine those two sorted arrays into a solution to the original problem? Okay, so let's assume we have already sorted the left and the right. So let's say our sorted left half is 3, 4, 5, 8, and our sorted right half is 1, 6, 7, 9. Okay, so how might we combine this into a solution for the entire array? So there is a trick. There is a trick way of doing this, okay? So the idea is to traverse both arrays at the same time in lockstep. Okay? So how does that work? So what we do is at each stage, let's say we have 2 pointers, I and j. So the ith element of the first array, ith element of the first array, and the jth element of the second array. Jth element. Okay? The idea is, this is the idea, okay? We first, let me get a new page. The idea is we first compare AI to BJ, where this is like array 1, array 2, right? So the idea is if AI is less than or equal to BJ, right? So if the ith element of array 1 is less than the jth element of array 2, let's say I and j are 1 at the moment, right? So if the first element of array 1 is less than the first element of array 2, then the first element of array 1 goes first, right? So we insert AI, okay? And increment I. This is the key. Increment I. And otherwise we insert bj and increment j. Increment j. Okay, so how does this even work, right? Let's actually do it on the actual arrays that we had in the last that we just had, which was 3, 4, 5, 8, and 1, 6, 7, 9. So let's do that. We had 3, 4, 5, 8, and that's array A. Whoops. Sorry, my paper has gone a bit wonky. There we go, that's better. We have 3, 4, 5, 8, and that is array A. And we have 1, 6, 7, 9, which is our array B. All right, so the first thing is compare 1 to 3. Compare these two, right? So compare A0 with B0, right? 1 is less than 3, so we insert 1, okay? Now we go up in this array, all right? So now we're comparing 3 to 6. Oh, but 3 is less than 6, so we'll insert 3 and move up. But what about 4? What about 4? 4 is also less than 6, so we'll insert 4 and move up. Now we're comparing 5 to 6. 5 is less than 6, insert 5, move up, okay? But now 8 is bigger than 6, so 6 is less than 8, so insert 6 and move up in B. 7 is less than 8, right? Can you see? 7 is less than 8, so we will insert in B and move up. 8 is less than 9. 8 is less than 9, so insert from A and move up. Well, we have nothing else left in A to compare to, so we only have B, and then we can just go through B, and we have 9. Simple, right? 1, 3, 4, 5, 6, 7, 8, 9. Cool. So that is how you do it. And this takes linear time. So the combining or merging step takes linear time. Because all we're doing is just looping through the arrays one at a time, basically, or in lockstep together, right? We're just looping through the arrays. That's at most 2n elements to loop through, which is O of n. Okay? So what is the running time of the entire algorithm? Well, that's a bit weird, right? So what's happening is, let's say t of n is the time to solve an input of size n. Okay? The idea is that we have to solve the left half, which takes t of n divided by 2 time, right? Because it's the time to solve a problem of size n over 2, which is the left half, plus t of n over 2, which is the time to solve the right half, a problem which is also of size n divided by 2, plus n. Okay? T of n, right? And we have tn over 2, which is the left, solve left, solve right, and combine. And you can show, I'm not going to show this, but it's not too hard to show. You can look this up, but you can show that if I have something like this, Tn is 2 times T of n over 2 plus n, and the time to solve an input size of 1 is just like, it takes one step, right? Because if you have a 1 element array, it's already sorted. So this is just basically a recursive equation, and if you can solve this, you know the running time Tn. If you know you can know the running time Tn in explicit form. And the solution is T of n is approximately order of n times log n, which shouldn't be too much of a surprise, right? We know that it's higher than n, right? Because just the combining step takes O of n time, right? So we know that it's higher than n, but if we just did a really simple comparison-based sorting, right? So if we just found the first element, put it to the left, found the second element, put that to the left, and so forth, if we did that type of sorting, that takes O of n squared time, right? The naive version, right? All we have to do is compare all n elements to each other, find the minimum, and do that repeatedly. That's O n squared. So obviously something like this, using this more sophisticated technique like divide and conquer, should be faster than O of n squared, but it should be slower than O of n, right? That's why it is n log n, right? And this makes a huge difference. So for example, if I want to sort 1 million elements, right? If I did it the naive way, it might take a few hours or more. Using the divide and conquer way, using divide and conquer, which is what all the libraries and all the normal programming languages use, it takes 1 second. Great. That is really nice, isn't it? All right, so now let's get on to something that's a little bit harder, all right? This is our kind of real problem for today. All right, here we go. Let's have a read. Okay, after the success of your latest research project in mythical DNA, You have gained the attention of a most diabolical creature, Medusa. Medusa has snakes instead of hair. Each of her snake's DNA is represented by an uppercase string of letters. Each letter is one of S, N, A, K, or E, so it spells out snake. Okay? Your extensive research shows that a snake's venom level depends on its DNA. A snake has venom level X if its DNA has exactly 5 X letters, begins with X copies of the letter S, then has X copies of the letter N, then has X copies of the letter A, K, and E, and so forth. So for example, a snake with venom level 1 has DNA S, N, A, K, E, right? Because it has 1 S, 1 N, 1 A, 1 K, 1 E, and 5 letters, okay? While a snake that has venom level 3 has DNA SSS, NNN, AA, KKK, EE. If a snake's DNA does not fit the format described above, it has a venom level of 0. Medusa would like your help making her snakes venomous by deleting 0 or more letters from their DNA. Now, given a snake's DNA, can you work out the maximum level, the maximum venom level this snake could have? Okay, so let's look at the sample input 1. Okay, let's look at sample input 1. We've got this this thing, right? K, S, E, E, S, and so forth, and it apparently has venom level 2. All right. So why does it have venom level 2? So what we can do is, well, we have 2 S's over here, right? 2 N's, let's say here and here. Here and here. Oh, sorry. Here and here. 2 A's. A K here. You got, oh, sorry, K here. A K here. And 2 E's, right? And you can delete some characters so that we just have 2 S's, 2 N's, 2 A's, 2 K's, and 2 E's. Okay, and they're all adjacent, right? So it begins with X copies of S, then X copies of N, then 2 copies of A, then 2 copies of K, then 2 copies of E. And you can delete all the other letters so you get that. Can you get 3, right? So can you have 3 S's, 3 N's, 3 A's, 3 K's, 3 E's, okay? Let's try that. So let's say I have the first S here, the second S here, and, well, and the third S is over here, right? It's the second last letter. Well, now we can't make 3 N's after that, or 3 A's, or 3 K's, or 3 E's, right? Pretty simple. So the answer here is 2. That's the maximum venom level of the snake. Okay, so the question is, how in the world can you figure this out fast, right? I mean, one idea is to actually try and find the maximum level by just going through the string once. That's pretty hard to do. I'm not gonna lie, it's pretty difficult to do by just going through the actual thing once to find the maximum level. Well, we knew it was 2 because we kind of knew the answer already. Does that make sense? Like, once we knew the answer was 2, it was relatively easy to check that the answer was 2, right? But if we didn't know that the answer was 2, how in the world would we figure it out? Okay, so that is actually the crucial insight of this problem, okay? So the insight is this is kind of where the creative thinking part of programming competitions comes in, right? The insight is, assume we already know the answer. Assume we already know the answer. Assume we already know the answer. Or or we have some guess at the answer. And I'm already kind of dropping hints as to what the solution is, right? Just by the fact that I'm saying that we have some guess of the answer. Can we check it, right? The question is, we can check it fast. We can check it easily, but we have no idea how to figure out the answer. Okay, that's insight 1, okay? Insight 2 is that if the snake, if the DNA has venom level L, it has venom level L minus 1, and also it can also have venom level L minus 2, and so forth up to venom level 1, right? So if we have something where we can delete letters and get something like S, 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 N, 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 A, 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 K, 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 E, 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 right? So this is venom level 3. So this is venom level 3. So this snake has maximum venom level 3, right? But, this DNA has maximum venom level 3. Let's say this is the maximum venom level. But then it also has venom level 2, 1, and so forth, right? Does that make sense? Like I can create a snake of venom level 2 from this by simply deleting all of these characters, right? Just by deleting some more characters, I can create a snake of venom level 2. So the idea is that if we know that the DNA is not venom level 3, it's not higher than 3, right? The venom level isn't higher than 3, isn't larger than 3, isn't larger. Now, this kind of has some similarities to our guessing game, remember? So, our guessing game kind of had similar properties to this venom thing. Why? So, for example, if we guess, say, 500 from our guessing game from 1 to 1000, and the number is lower than 500, it's definitely lower than, say, 510, or 600, or 800, or anything from 500 to 1000, right? In the same way, if the DNA has venom level L, it also has venom levels 1 through to L minus 1, right? L is the maximum venom level, right? And if it's not venom level L, then it's definitely not anything larger, right? So if it's not, just like if the number is less than 500, if the number is lower than 500, it's definitely lower than 510, right? So there's kind of an ordering property that's very, very important, that is shared between the guessing game and the venom levels, right? Try and understand this. Try and think deeply about this. And in fact, all algorithms where binary search works has this sort of property, and they call it the binary search property. You should look this up, but that's the point. Anyway, so what we can do is we can devise a test based on this. So the idea is we guess the venom level. Guess venom level exactly like we guess numbers in the guessing game. So we start with a lower bound of venom level 1. Venom level 1, right? That's our lower bound. And what's our upper bound? Right? Is there a way to find the maximum possible venom level that we should be able to search? Well, that's actually pretty easy. We know that every piece of DNA, to have a certain level, needs to contain X letters of type S and so forth until X letters of type E, right? So if we want to be the most efficient with our letters, right, for a given venom level, right? So for say venom level 3, or sorry, for venom level 2, the most efficient DNA of venom level 2 has length 10, right? Because it's just S, S, N, N, A, A, K, K, E, E, right? This is the most efficient way to make DNA of venom level 2, right? Does that make sense? In the same way, if we have some length, say we have, this thing has length 10, right? The maximum possible level, we don't know if it has that level, the maximum possible level it could have is 2. Is in fact, it's the floor of 10 divided by 5, which in this case is 2, right? If it was 11, it would also be 2, because 11 divided by 5 is 2 and a little bit, which rounds down to 2. Fair enough? So this is an upper bound, right? This is an upper bound. Does that make sense? Do you understand why a piece of DNA with 10 letters could not have venom level 3? Well, the reason why is because to get venom level 3, we will need at least the following letters, right? We will need at least S, 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 N, 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 A, 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 K, 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 E, E, E. And that's 15 letters. That's not enough to make venom level 3, right? Because we only had 10 letters in our DNA to begin with. And we can only remove letters, we can't add them. Does that make sense? Cool. I hope it does. So the upper bound is 4 of length divided by 5. And what we're going to do is we are going to implement a binary search test, right? So we will make a checker for the levels to check if something has venom level L, right? Or if it possibly could have venom level L, and if not, and if it has, if it has venom level L, we'll find out. And using that, we will binary search the maximum venom level. But I think that's enough for today. We will continue tomorrow with this implementation. On Monday with this implementation. All right, thanks everyone.